Okay, thank you. So let's resume our discussions on exclusion processes. Yeah, so yesterday we studied the fluctuations of TSEP for particular initial condition called the step initial condition. And we showed that if we scale the fluctuation of the current at the origin appropriately, then we get the GUE trace rhythm distribution. And the main part of the proof is to show that for such a distribution function for the TSEP problem, we get some expression which is very, very close to the largest eigenvalue distribution for GUE, right? That's fine, but the way we show this to start from the Green's function, transition probability, which was found by using beta ansatz, and then try to rewrite it in such a way that we can see some connection to random matrix theory, right? But it was probably you may have thought that the calculations are not really motivated. It's not so clear why we have to do such calculations, right? But after doing some calculations, we arrive at such expression. But in fact, now there is a, well, this was already a pretty old thing, but there is a better way of looking at things. So today we start from that. And another question is how much we can try to generalize such calculations, arguments to other models. At the beginning, I explained that there are various models, not only TASEP, but general ASEP, QTASEP, and there are also many other similar processes. So the natural question is, can we study many models with basically the same calculations, or we have to do something different, or it's just impossible? So today, at least, we study how we can study QTASEP case. General ASEP is also studied in a similar way, but QTASEP is a bit simpler. So today we just focus on QTASEP, continuous time. Yeah. And yeah. So today in this lecture, I think I try to convince you that QTASEP and TASEP are pretty similar. Of course, some people know that there's a huge gap between TASEP, which we learned yesterday, and the QTASEP and TASEP. So the TASEP we learned yesterday is more related to free fermions, determinant of point process, but QTASEP, ASEP are usually considered to be more difficult. But it is true, but if we look at things in an appropriate way, I think they are pretty similar. So this is what I want to explain today. Okay, so today finally we come to section 2, part 2. This is about Shu and Q Whittaker processes. So usually, maybe this part and this part can be in a separate section, but I'm hoping that they can be in the same section. Okay, so today's reference for the lecture today is basically this paper of myself with Takashi Imamura from Chiba University. And basically this is about stationary QTASEP, but of course if we put some parameter to 0, we can also study the step case. Yeah, in the whole lecture, basically, yeah, we stick to the step initial condition for simplicity. This already appeared in PTRF, and archive number is here 2 years ago. So yeah, if you are interested or if you have some problems to understand, you can take a look at them. Right, and then first we start from the Schur case, which is directly related to TASEP. And the Schur function you learned last week very, very in detail, I think. So I wanted to skip some of them, so I already tried to write down some formulas already. So Schur function denoted by S lambda of x. So yeah, here we simply take n variable case, x1, xm, which is written as collectively as X. This is, so there are several definitions as you learned last week, but one definition is a combinatorial one, which is written here. So shear function can be defined as a sum of a semi-standard Young tableau with a shape. So this is for skew case, lambda over mu. And we take a sum of monomials, x1 to the power number 1 in semi-standard Young tableau times x2 to the power number of 2 in semi-standard Young tableau and so on. This you learned last week, yeah. And I think you also learned that there is another formula called Jacobi-Trudi formula, which writes the shear function, also for this skew case, in the form of a single determinant using complete homogeneous function, right? Yeah. Okay. So this is a definition for the general n variable case, but we can specialize to the one variable case, in which case this gives you a very, very simple formula, which looks like this. So this is still general, lambda and mu, but we consider one variable case. In this case, there's only single factor, and in fact, so this condition gives you just a kind of indicator function for lambda and mu, which should satisfy this condition. And this is just an interlacing condition. Okay. And there's a power, x1 to the power number of boxes of lambda minus mu. Sorry. And then by using this, one can see that the shear function for the usual partition for n variable case, sorry, maybe this, yeah, for n variable case, so there's a kind of recursive structure for the shear function. And then there's also Cauchy identity, which you also learned, I think, last week. Yeah, so X is n variable case, and Y has m variable. In this case, the product is finite, and yeah, this is given by this. There's also, did you, Taurus scalar product? No, okay. Yeah, so there are some inner products for the shear function. One of them for n variable case is a so-called Taurus scalar product. So this you didn't learn. Sorry, I don't give you a proof of this. Yeah, this is written in a standard textbook. Okay. So there is a kind of orthonormality relation for the shear function for n variable case. If you take this function to be given by this. Okay, then using Cauchy identity, this torus scalar product, one can find integral representation of a shear function. Yeah, basically you multiply, first you set x to be 1 over z, and you multiply m of z and take this integral. Then from the Cauchy identity, only s lambda y remains, and then we have some integral here, right? So this is the kind of usual shear function, but we can consider so-called various generalizations for the shear function associated with more general specializations, so-called specialization. And this is corresponding to generalizing this pi function. And maybe we can introduce some shear function depending on 3 sets of parameters, alpha, beta, gamma, by using this kind of integral formula. Right. So this is one generalization. If you take, what is that, beta to be 0, and if alpha 1, blah, 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 alpha n to be yj's, and rest is 0, then if this is also 0, then this is gives you back to the usual shear function, but this is can be considered as some generalization. But here, we simply consider the case in which so in the following, we simply consider the case where this factor do not appear, and we only keep this one. And gamma is replaced by t. T will play the role of time, but yeah. And then in this case, we write this shear function to be simply by s lambda of t. So this is simply defined by this formula, right? So this corresponds to the so-called transitional specialization. And in this case, in fact, this is known to be also written as simply written as t to the power size of lambda divided by lambda factorial times f of lambda. And here this f of lambda is the number of standard Young tableau with shape lambda. But this formula we don't actually use. So this integral formula is enough for our purpose. But anyway, so this can be written like this. Then, for example, one can check that this satisfies very simple relation like this. Here lambda 1j means that, so this means only lambda j is, we subtract 1 from only lambda j. So all others have the same number from as the original lambda, but only if you write like this. So yeah, if this is j. So if this is lambda, lambda 1 minus j means that we remove one box from the j. And we do this for each row. And we take a sum. And in fact, this formula can be shown by applying the exercise from yesterday. So yesterday, 218, right? Yesterday you showed some formulas similar to this one, right? And if you put it to this definition, yeah, you use the formula you proved yesterday in the exercise to this part. So you take a derivative with respect to t. So then this comes down, and then you can use the formula in the exercise to show this is right. Okay, so this is a kind of preparation for yes. Sorry. Cannot remove a box. Oh, but then it should not appear. Yeah. So this means that if you have if lambda is like this, then you should remove up to here.
Two equal parts of lambda.
Two equal parts of lambda. Like this. So then this. Equal one. This is right. Okay. No, something's wrong. Your function is 0. I see. Oh, so in this case, we should interpret this as 0. Sorry. Okay, then we consider so did you run Gelfand settling pattern last week? Gelfand settling? No. Okay. So yeah, this is easily seen in the figure. So in a triangular shape, maybe we start from lambda 1, 1. Above it we have lambda 2, 1 and lambda 2, 2, and so on. And the reason why we write this as a triangular shape is that we want to have some inequalities for the size of these values in such a way this is consistent with this triangular shape. This and 3, 1, 3, 2, 3, 4, yeah, 3, 3, and so on. And this should be bigger than this. Like this. So as a definition, we define a Gay-Van-Tettering cone of size n to be given by a set of values, lambda ij, which satisfies these conditions. And pictorially, this can be represented as a triangular shape. Then we consider some Markov dynamics on this Gay-Van-Tettering cone. So basically, each lambda ij tries to hop in the right level place. So yes, yeah. With rate 1. Poisson random walk here means that it should be considered as a single species Tarset particle hopping in continuous time only to the right with rate 1. But if we do this for all particles independently, then we cannot keep the condition of Gay-Van-Tettering. So we have to keep them somehow. How do we do that? If if this lambda ij and lambda I plus 1 j plus 1 are the same at some time, then to preserve this ordering, this particle cannot move. So there is a kind of this is a kind of hierarchical particle system. So the lower, the stronger. So they have the lower, so small lambda ij's with smaller I has priority, right? So when they are at the same position, so in the triangular shape, they are like this, but the condition is like this, including equal. So sometimes maybe they are at the same position, right? So when this wants to move, this is fine, but when this wants to move, then this is not allowed to preserve the Gay-Van-Tettering condition. So this is this rule. So in this sense, this particle is blocked by this particle. Right? Are you following some question? Okay. On the other hand, if so originally these two particles are like this, but maybe sometimes they are at the same position at a given time, then so this particle has a priority because this is at a lower low. And when this particle wants to hop, if this happens, then the order of the Gelfand settling is not satisfied. So in this case, we have to postulate that this also has to hop. Right? So this is sometimes called push. So this is push. So yeah, because of these two, and if we put these conditions, rules, then we can see that this Gelfand settling condition is maintained for the whole time. And in this way, we can define Markov process for Gelfand settling. And this is sometimes called block push dynamics. Right. And one can write down the forward equation, master equation. For example, for the case of n equal 2, of course, this is pretty similar to the case of thesis, right? So depending on particle configurations, we wrote down some evolution equation for the probability, and we can do something similar here. So P of lambda 1, 1, 2, 1, and 2, 2 means the probability that they have these values, and we take a time derivative. And then, just as in the case of thesis, there are some incoming possibilities depending on each particle's hop. And also there is a contribution with minus sign corresponding to the outgoing process from this configuration. And there are other cases when this and this are equal, or this and this are equal, or all of them are equal, right? So, and I hope you can write them down, all of them. And the exercise problem, yes? Sorry. Is sorry? Yeah?
There are weak inequalities because these are partitions.
No, no. So in this case, but here we want to consider other cases. Then some of them doesn't disappear, doesn't appear in a similar way to the tacit case yesterday. So please write them down to save time. And this is what we want. No, it's okay. Sorry, not yet. So please write them down, right? For the case so there are three other possibilities. These and these are the same. These and these are the same, and all of them are the same. And then you have to take into account this broke and push rule. Okay. Why we are considering this dynamics? Because in this dynamics we see cases. Now we have defined some Markov dynamics on the whole Gelfand-Tettering cone in the triangular array. But maybe we can focus on this diagonal line on the left. Then one can see that in fact this line evolves independently from other parts. If you consider this block and push mechanism, they are evolving independently, autonomously. Then the interaction among these particles are just blocking, right? And then, of course, in this original process on Gelfand-Tettering cone, they could have the same value because this contains equality. But if we shift these numbers by 1, 2, 3, and 4, then this blocking mechanism is nothing but exclusion condition for these particles. More precisely, so this is the state. Right? If you shift lambda jj, which are on the left diagonal, by j, for j between 1 and n, then these xj's are evolving like tacit, which you know very well. Okay. Now we also have to specify the initial condition. So the simplest case is to take all of them at t equals 0 to be 0. In the language of TASEF, because of this shift on this left diagonal, this corresponds to step initial condition, right? But on the Gelfand-Tettering cone, we take all of them to be 0 at the beginning. Then we can ask the probability that at time t, what is the probability that we have these lambda ij? And remarkably, this probability can be described explicitly in terms of Schur function. And this is given by no, sorry. Okay, I want to generalize a little bit. So the probability of having lambda ij's is given by this expression. So this is just a product of s lambda 1, s lambda 2 over lambda 1, sorry, with but in fact, we could also introduce a dependence in this dynamics. So for each row, we could associate the hopping rate aj. Then we could define the same dynamics. And in this case, for this same initial condition, the probability is given by this. For the particular case I explained there, all of the rates to the hopping to the right is 1. So if we take all of them, aj to be 1, then this is the probability for that dynamics. And the exercise 1b, 2.1b is to check that this measure satisfies this dynamics for the case of n equals 1. And in this case, this normalization z is simply given by this product of expansion. Yes. Yeah. One interesting remark here is that if we start from this measure on the Bayes-Van settling pattern, we can consider some dynamics which is satisfy this measure, right? One example is, of course, this drop push dynamics, but it is known that there are various possibilities of dynamics which preserves this measure. And some of them are related to so-called RSK algorithm dynamics. And so this is for the kind of sure case, but for more general setting, this kind of problem was studied by Okonelpe, Borodin Petrov, and Matveev Petrov. There are several papers on this, and this is very interesting. But today I don't go to that discussion. At least for this drop push dynamics, so this is the measure for at time t. Right. So suppose we are interested in TASEF, in particular nth particle position, which is related to the current, as in yesterday, then it's here. Now we have dynamics on this whole Bayes-Van settling cone. If we are only interested in this particle, maybe instead of looking at this diagonal line, maybe we could focus on this line and study this particle as a marginal of this n particle system. Right? And in fact, one can see that this is also kind of independent object, can be considered as independent object. And this is related to the Schur function, the Schur measure. And this is easily seen from this measure. Going to the marginal for the top line corresponds to take a sum over lambda 1, lambda 2, and so on, except for this last one, lambda n. And by the definition of the, by one formula which I wrote down today, it is easy seeing that if we focus on the marginal for lambda n, it is simply given by a product of two shear functions. Sorry, yeah. So this measure on the Gelfand-Settling cone is for shear process. Some special version of special case of shear process, and of course there is a version in which you see the usual m variable shear function here for the shear process, but this is one version of the shear process. And if you focus on the marginal on the top line, this gives you some measure on partition given by a product of the two shear functions in this way, and this is called a shear measure. So then, yeah, to study the nth particle position of Taysef, we can simply try to study lambda n of this measure, right? And as I wrote down at the beginning of the lecture today, there is a Jacobi-Trudi identity which allows you to write down this shear function as a single determinant. So now this measure has a form of a product of two determinants. So from yesterday I was stressing that the measure in the form of a product of two determinants is very, very nice. One can apply very standard procedures to study various properties, right? And this shear function has such properties thanks to this Jacobi-Trudi identity. And by using this fact, one can study tacit nth particle fluctuations. This is a kind of more conceptual way of understanding the appearance of the random matrix type expression for the problem of tacit. Yesterday we started from the Green function, which has already nice structure of determinants, but the indices are a little weak. But after doing some calculations, we could arrive at determinant times determinant formula type expression. But if we discuss in this way, before doing real calculations, we can see determinant structure corresponding to Taysef. But this is pretty non-trivial, right? Originally, we are interested in this part. For this part, we don't really see determinant structure. But if once we go to this part, then we see determinant structure more in an easier way. So in a sense, the calculations we are trying to do yesterday is to start from some formula on this diagonal, and then do some calculations by introducing auxiliary variables. And then after taking sum over these variables, then we could arrive at this point. But in this way, we can see such a structure in an obvious way. Right, so this is all for the shear case, tacit case. Then, as you probably know, the shear function can be considered as some special case, limiting case of more general multivariable functions like McDonald polynomials, Jack polynomials, and so on. In this lecture, we focus on one particular generalization known as the Q-Hoitaka function. So this function includes Q. So there are many formulas which include Q factorial and so on. But today I already explained in a note I distributed yesterday. So for basic definitions, you should take a look at the notes. Maybe in this, so I try to explain these things in a very parallel way to the sugar case. Maybe in this case, we start from one variable case. In the one variable case, the Q Hoitaka function is defined in this way. And when Q is equal to 0, basically this vanishes, but this part gives you some condition, and this becomes lambda, this interlacing condition for the sugar case. But with Q, so this we have to include. But yeah, at this point, this is not so complicated, I think. An n variable case can be defined in the same way as for the sugar case. So this is a sum over lambda 1, blah, 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 lambda n minus 1. Almost identical to the sugar case. Then, yeah, so here is some difference from the sugar case. In the sugar case, Cauchy identity is satisfied for the same function s lambda, but for the Q case, we have to modify one of them a little bit with this Q factor. This is also related to some normalization. Anyway, by introducing almost the same function with coefficients slightly different, so this is denoted by Q, then if we take a sum over P times Q over lambda, then this has a nice property. Of course, when Q is equal to 0, Q lambda becomes P lambda. Both of them are shear functional. And then, so this is Q infinite product. When Q is equal to 0, this becomes just a 1 minus xi yj. So this is the shear case. But with Q, this is the formula. There's also a torus scalar product. So this is a kind of orthogonality relation for Q-Hoyteka function for n variable case. Hmm? Two factors?
Ci over Cj and Cj over Ci?
This, you mean this one?
Yes.
Yes.
You said Q equals 0, you get, but in the Schur case it was 1 not. Oh, okay. It was I not equal to J.
Yeah. Okay, yeah.
Okay.
You can write it like that. Sorry. Yeah. Then by using this Cauchy identity and this Stoller scalar product, one can write down some integral formula for Q-Hoyteka function. And in fact, we could introduce, we could also introduce generalization corresponding to more general specialization. But in our discussion, maybe we can just consider the case corresponding to the Plancherel specialization, which corresponds to yeah, it's really almost the same as for the Schur case, right? So of course, at various places we have to include some coefficients, including Q factorial, but otherwise the structure is really the same. And then this also satisfies. Maybe I can write it down. So this satisfies this kind of relation. And in the case of Schur, this was not present, right? But now we have something which depends on Q. And now we can consider, we want to consider some Markov dynamics, again on the Gelfand-Tettering cone. And here, I don't really explain how they are really defined, but I just mentioned that there is a Markov process. Such that if we look at this part, we see Q thesis. Maybe with parameter A. We also take the initial condition to be the same. All of them start from 0. And then in this case, there is a dynamics. This is, of course, a generalization of the block push dynamics for the T-set case. And the probability of having some configuration lambda ij at time t is given by this expression. And this is called Q-Hoitaka process. And in a similar way, to show that the Schur process satisfies the dynamics of the block push dynamics, you can try to start from this Q-Hoitaka process now to see what kind of dynamics is satisfied by this measure. Right? And for the case of Schur, I think I mentioned that one should use this kind of formula to see how the dynamic block push dynamics is satisfied by the Schur process. In this case, of course, we do the time derivative, so we get time derivative of this object. And in this case, we have to use this one. And then, of course, there's a big difference of this factor. And this depends on q to the power lambda j minus lambda j plus 1. And if you remember the dynamics of Q-T-set, there was so the hopping rate to the right was really in this form, right? Yeah. The hopping rate in the Q-T-set was prescribed to be given 1 minus q to the power gap. And gap was xj minus 1 minus xj minus 1. Right? And now there's a shift. So then this is basically the Q-T-set rate. Yeah, but if you consider these parts, the rates become a bit more complicated. But basically, by using this kind of properties of the Q-Hoitaka function, then one can see what kind of dynamics is satisfied by this measure as a generalization of the block push dynamics for Schur case. Right. As in the case of T-set with q equals 0, if we are interested in Q-T-set, in particular nth particle position, then instead of considering diagonal dynamics, we can focus on top row. And in this case, by the same argument as for the Schur case, this gives us the so-called Q-Hoitaka measure now. So now we can try to go on in the same way, but here it's a bit different from the previous case. Because in the case of Schur, so the fact that each Schur function can be written as a single determinant due to Jacobi identity was crucial. So what about the case of Q-Hoitaka function? Unfortunately, or fortunately, there's no formula like that. So nobody has succeeded in finding some single determinant formula for these functions. If these are written as single determinants, then we are in good shape, right? We can simply apply the standard techniques of determinant of point process, free fermions, to study the properties, but this is not possible here. So what can we do from here? But of course, on the other hand, Q-Hoitaka function or McDonald polynomials in general are known to be very, very good multivariable polynomials. So people have thought about various approaches. And there are many things one can do, in fact. So one possibility is to use the known properties of the Q-Hoitaka function for McDonald polynomials. So for example, there is an operator which is diagonalized by this Q-Hoitaka function. And these operators and also eigenvalues are known. So if we want to consider some average of with respect to some information about lambda, maybe we can use this kind of information. And this was really the approach taken by Borodin and Corbin. In the very famous paper, McDonald process, right? So this is one successful approach. I don't know. Another well-known and quite useful approach is the I don't know what is the standard names, but maybe I can call this replica Bethe-Ansatz approach. A replica is some methods to study the KPZ case, but maybe this can be replaced by duality. About duality, I mentioned a little bit for the symmetric exclusion process case, right? And in that case, a one-point function for the symmetric exclusion process satisfies very simple equation. In particular, this is closed equation. And for the case of Q-T-SEP, if you look at density variable, this does not satisfy some closed equation. But if you look at Q to the power position particle, in fact, this satisfies closed equation. And this is also a manifestation of the kind of generalization of this duality for the Q case. And by using this, one can then n-point function of this type satisfies n-particle dynamics of Q-T-SEP again. Then Q-T-SEP is also known to be solvable by Bethe-Ansatz, as we did yesterday. Then by using that, one can do something. And anyway, in both approaches of McDonald operators and duality Bethe-Ansatz approach, what we do usually is to first write down this moment, Q-deformed moment, and then by using this Bethe-Ansatz, like yesterday, we can find some n-fold integral formula and then we consider generating function of this. If you use Q binomial theorem, this can be expanded in terms of this moment, right? So in that sense, this can be considered as a generating function for this Q moment. Then after sum means pretty long calculation, one can arrive at a Fredholm determinant expression. The final expression is in a sense, very similar to the T-SEP case. For T-SEP case, by using standard machinery from random matrix theory or free fermions, determinant point process, we could see that the final result is given by Fredholm determinant. The situation for QTSF, ASF, this is very different. Even though we can arrive at the Fredholm determinant as a final expression for this particular quantity, in the intermediate step, we don't see any determinant of structure. So, but we can use some other methods to arrive at this value. So we want to have a better understanding. We still want to have a better understanding, I think. But yeah, this is still, I think, the situation. But these methods have been very, very successful to study various problems. Yeah, okay, sorry. So one reference for this duality-based ansatz is BCS, Borodin, Kovin, and myself. Looks like a paper for superconductivity, in fact. Not. But this is also a nice paper about this duality-based ansatz. And in this paper, we already mentioned that, so in this paper, we basically studied only step case. And we also mentioned that if we introduce some parameter, we see that this moment diverges. So then we cannot take this route to study the distribution, right? So this is the reason why I wanted to consider another approach. So today, and in the paper I mentioned at the beginning of today's lecture, in the Q stationary Q-TSF paper, we use slightly different approach. Well, this is, in fact, it's pretty simple method, but let me try to explain. It's very simple. So the idea is very simple. So as I said, for the random initial condition for the Q-TSF case or ASF case, Q moment diverges. So we cannot really use the moment. But the quantity we are really interested in is this generating function, or this is sometimes called Q Laplace transform, because this can be considered as a Q deformation of the usual Laplace transform. So this is the quantity we are actually interested in. We are not really interested in moment, right? So maybe we can try to find another way to study this quantity directly. Then at some point we noticed that in fact one can write down rather simple formula for this probability itself. So this is our approach in the paper. These capital A and Z's are just a product of the small ones. And, so this is again simply given by this exponential product. So yeah, we found that there is a simple formula like this for the probability itself. How can we prove this formula? It's also pretty simple, in fact. second part here? Here? So this is kind of pi function, which appears on the kind of right-hand side of the Cauchy identity. And in this particular, so yeah, so, this is not a product here. So this is a kind of pi function. Right. Yeah, yeah. But, well, yeah, in fact, one can consider other specializations in a similar way. But this is corresponding to the continuous time Q cases with safe initial conditions, so I'm sticking with it. Yes. So the idea is very simple. We just rewrite the Cauchy identity, you know very well, in a slightly different manner. First, we rewrite the Q-Whittaker function, which depends on lambdas in such a way that lambda independence is separated. By looking at the definition and some examples, you can see that, in fact, the Q-Whittaker function can be rewritten in this way. And the lambda independence appears just in this way, where x is just a product of xi's in these variables. And then the remaining dependence on lambda is in the form of L, which is just a collection of L1, blah, 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 L minus 1. And each Lj is just a difference of lambda j. And then we plug this simple rewriting of the Q-Whittaker function in the Cauchy identity I showed you. Then so we can rewrite the Cauchy identity in terms of R now. Now we have only a sum over L. So we can keep the information of lambda n. So we don't take the sum over lambda n, right? We can still keep it as a variable. Yeah, then one can easily check that the Cauchy identity can be written in terms of RL in this way. Of course, so this is the usual kind of normalization. Cauchy plot, the right-hand side of the Cauchy identity. And if we rewrite this, then again we can take sum, then we get this product, infinite product. Anyway, this is what we do. Then sorry. No, before that, sorry. Then, Yeah, now we want to really calculate this probability from the definition. Yeah, if we take the whole sum over lambda, this gives us, of course, 1. But now we put a restriction on the lambda n value. And then, so this is, this has this integral representation, right? Then we see a sum over lambda of p lambda with this condition. Now, for this part, here we use the rewriting of p lambda in terms of r. Then we see that and then this is exactly the sum which appeared here. Right? So then if you plug this into here, yeah, I think you already arrive at this formula. So in this way, we can write down some integral representation for the probability that lambda n is exactly equal to L. So once we have a formula for this probability, then by definition, we can try to calculate the Q Laplace transform. So this is, by definition, this average is given by this expression, right? Now we have a formula for the integral formula for this probability. And we simply put it here. And then one small remark is that, so in our case of state initial condition, so this sum over L runs from 0 to infinity. But of course, if you would negative L, so this probability is 0. So this can be replaced by minus infinity. So this is the sum of the whole Z. And then sorry, but these are just the same as before, so you can take a look at it. So yeah, now this Laplace transform formula has n-fold integral formula like this. But there's a remaining sum here. Yeah, okay. Yeah, one remark here is that, of course, we are very interested in this probability, right? And L dependence is crucial. But the good point of this formula is that the L dependence is quite simple here. L just appears as power here. So when we take a sum over L, so this just appears as this kind of power. And of course, we have to take a sum divided by this stuff. And if this sum cannot be taken, then we cannot do how to proceed. We don't know how to proceed. But fortunately, as you checked yesterday in the exercise, this sum can be taken by thanks to the Ramanujan formulas. Yeah. Then so this is can be written as so these theta functions are also defined in the note. So then this disappears, and then we arrive at the formula. So now we have a formula for this Q Laplace transform in this way, without going through moment now, right? So now, if we can see nice structure here, that's good. Now, 3 minutes. I have to skip many things. Yeah, so maybe here I want to mention one thing. So maybe for you, this looks already almost formidable, right? Looks pretty complicated. But maybe it makes sense to try to see what's happening in the Taysef case, which corresponds to Q equals 0. So in the usual approach of replica-based ansatz, duality-based ansatz, then we consider Q moment. So it is pretty difficult to take Q goes to 0 limit, right? But nice thing about our approach is that we don't use the Q moment. So at any point we can consider Q, the usual Taysef limit, Q goes to 0 limit. And if we take Q goes to 0 limit, so as you learned in the exercise yesterday, this becomes, well, if you take appropriate limit, this really becomes, so the quantity you studied yesterday. And here, from here you get times Ci to the power n. And then the remaining is rather simple. So Q equals 0 case, yeah. So from here you get, so this corresponds to the case of Schubert. So now you have Ci Cj. And there are something. But anyway, this is already pretty good expression because, at least, yeah, sorry. So this is just a kind of potential term. This part is easy. The main factor is here, which includes some kind of interaction, I and J. But this is very good because basically this is given by this product of difference squared. So now we see product of determinant structure inside this D integral, at least for the Q equals 0 case. And this has a very similar form as in the case of largest eigenvalue distribution of GUE, right? In the case of GUE, the measure was xi minus xj squared something. And we are also taking the integral of xi, right? And in this sense, this is very similar. We have square of Gantelmann determinant, and then we take integral. Basically, we can do the same calculation as in this case to arrive at the first determinant formula. The question is what's happening for the general Q case, right? So yeah, in the Q equals 0 case, this is very simple. But in this case, in the case with general Q, so this was Q product. But there is a way of rewriting this Q product in two separate factors. Then I will finish in a few minutes, so give me a few more minutes to finish. By rewriting this infinite product, Q product, in an appropriate way, so this here, then the whole Q Laplace transform can be rewritten in this way. Here there are some factors only depending on I, but this is not so important, like a potential term in the Gaussian case. Anyway, so this is the important structure. And when Q goes to 0, this part becomes identical to this part. And then, yeah, by using Cauchy determinant identity, this becomes determinant. In the case of Q equals 0, this has the same, this is exactly the same as this, so this is of course determinant. But now for the general Q case, we have something similar, but using theta function. But remarkably, so here I said that we use Cauchy determinant identity, but Cauchy determinant identity is known to be generalized to various cases, but there's a kind of not general case, which includes theta function. And this exactly fits into that case. And this Cauchy determinant identity for the theta function is known as the Frobenius determinant. And this structure fits completely well to that Frobenius determinant. And in this way, this can be also thought of as determinant. And then now, inside this D integral, we finally have determinant times determinant structure for the Q asset case, right? And in this way, after after that, the calculations are, in principle, that's really the same as the Tay-Seth case. Then we can arrive at Fredholm determinant formula. And then we can do the kind of standard asymptotic analysis, as I mentioned for the Hermit case. Okay. Yeah, sorry, the last part may not be so clear. May not, yeah, but I think at least I could tell you about the main ideas, how to study the Q case, at least for the Q Tay-Seth case, in a pretty parallel way to the Tay-Seth case. Yeah. Okay, so yeah, about the exercise, I think you can now go to the all problems of second set of problems, and the deadline is today, right?
Tonight, yeah.
Tonight, yeah. Mm-hmm. Yeah.
It's posted, yeah, it's posted exactly as till the end of the second section.
Mm-hmm. Yeah. Mm-hmm. Okay, tomorrow I'm going to talk about some generalization in another direction, so two species case. Okay, thank you for your attention.